For the next part, I'm going to show you the other methods on how we can represent relations. There are two other methods we can use to represent relations. The first one uses 0-1 matrices, and the other one uses directed graphs, or also known as digraphs. Let us first see how we can represent relation using 0-1 matrices. The relation can be represented by using this method, where we have value of 1, if the ordered pair is in the relation. Otherwise, we put value of 0 if the ordered pair is not in the relation. Let's see our first example. Given A, with the elements 1, 2, 3, and B, with the elements 0, 1. R is the relation from A to B, containing the following condition. What is the matrix representing R? First off, list out all the ordered pairs in the relation. From the question earlier, we can see that A has 3 elements, and B has 2 elements. From this information, we will get a 3x2 matrix, which is like this. So, how do we get this matrix based on the relation? Let me show you a simple way to answer this question. From earlier, we know that we will get a 3x2 matrix. To make it easier, you can first write down each elements of A, on the left side, and B, at the top of the matrix. You can then fill in with value 0 or 1, according to the ordered pairs in the relation. Let's do one by one. Does 1, 0, belong to the relation? Yes. So, it is 1. Next, does the ordered pair 1, 1, belong to the relation? No. So, we put 0. Proceed with the next one, which is 2, 0. It is in the relation. And then, same goes to the others. Let's see our next example. Let A be the set, with elements A1, A2, A3, and B, with elements B1, B2, B3, and B4. List out the ordered pairs, from the relation R, represented by the matrix shown. To make it easier, you can list out the elements of set A, on the left side, and B, at the top of the matrix, like we did earlier in example 1. Then, pair the elements accordingly, and the answer would be a relation with its ordered pairs, A1 B2, A2 B1, A2 B3, A2 B4, A3 B1, and A3 B3. The properties of a relation can be determined by using square matrix. Recall that, if a relation is reflexive, then A, will always be in the relation. In a matrix, this means that the first diagonal is all 1. Next, if the relation is symmetric, what we are looking at is, if AB is in the relation, then it implies that BA is in the relation. To determine from the matrix, we can imagine, as if folding the matrix, along our first diagonal, and it should match up with each side. Or, our matrix is equal to its transpose. For a relation to be antisymmetric, we need to look if AB is in the relation, and BA is in the relation, then, it implies that A is equal to B. To determine visually using matrix, it means that either Mij has to be 0, or Mji has to be 0, or both, but they can't both be 1, otherwise it is not antisymmetric. Let's now look at the Boolean operations on matrices. For a union of two relations, we use Boolean or joint. As for intersection of two relations, we are going to use Boolean and, or meet. For example, the relation R and S are represented by these matrices. What are the matrices, representing R, union S, and R, intersect S? Basically, we need to perform the Boolean operation, as usual, one by one, from the first value in the matrix until the last value. And the answer would be like this. How do we represent composite of two relations? Suppose the relations R and S are defined by their matrices. The composition of these two relations is denoted by S.R, and it is actually represented by the product of matrix R and matrix S. Like we discussed earlier, the multiplication of logical matrices is performed as usual, except that Boolean arithmetic is used, which implies the following rule. Let's see an example. Consider set A, with its elements, A, B, and set B, with the elements, 0, 1, and 2. And set C, with element X, and Y. The relation between sets A, and B, is given by R. While the relation between set B, and C, is defined by S. To determine the composition of these two relations, we represent the relations by their matrices first. Then, the composition of the two relations is calculated as the product of both matrices like usual. Finally, we are going to discuss the second method to represent relation, which is using directed graphs, or also known as digraphs. This graph consists of a set V of vertices, together with a set of E of ordered pairs of elements in V, which is called edges. Let's say, for edge A, B, the A will be the initial vertex, and B will be the terminal vertex. We use arrows to display the graphs. Focus on this example. Display the digraph, with V, containing elements A, B, C, D, and E, with the following ordered pairs. How to create a digraph based on these two sets. Let me show you a simple way to do it. First off, draw each of the vertices, in a correct manner. Then, simply draw the arrows starting from the first ordered pair, and that is, A, B, which means, A, maps to B, and then, proceed with the next ordered pairs. If you notice from this digraph, the edge, B, is called a loop. If let's say, the loops are present, at all the vertices, then this relation is reflexive. So, that's the end of this subtopic.
Properties of relation, I'm going to talk about reflective, irreflective, symmetric, antisymmetric, asymmetric, and also transitive. Let's see what is reflective. To know that if a relation is reflective or not, our R must consist of all pairs, which is the first element in the pair and the second element in the pair must equal to each other. Alright, so let's say that we have set A, which is 1, 2, 3, and 4. So the reflective relation of this set must have all 1, 1, 2, 2, 3, 3, and also 4, 4. All of it must have inside of the R. So then what about this? Let's say that we still have the set A, which is 1, 2, 3, and 4, and between these three relations, which one is reflective? So we have to find which one amongst these three has all of the elements that being reflected, meaning that the relation that have all 1, 1, 2, 2, 3, 3, and also 4, 4. The answer is R2 because it has all the pairs even though it has 2, 3. The relation is still considered reflective because it already satisfies the condition. What is irreflective? Irreflective is a relation if every element in R is not reflected to itself, meaning that the first element of your pair cannot be equal to the second element of the pair. Right, let's say that we have set A, which is 1, 2, 3, and 4. We cannot have inside of our R 1, 1, 2, 2, 3, 3, or 4, 4. Even one of it cannot be inside of this. Going on to symmetric, a relation is called symmetric if the pair AB has the flip version of it, which is BA. Let's look here. Why R2 is symmetric? Because the pair of 1, 1, if we flip it, still becomes 1, 1. And we can say that if A is equal to B, it is always reflective. Next, we have 1, 2, and the flip of this is 2, 1, which is also inside of R2. So, both of the pair is inside of the same relation, so we can say that R2 is symmetric. Same goes to R3. Moving on to antisymmetric, a relation is called antisymmetric if the pair does not have its flip, which means that inside the same relation, there is no BA to AB pair. But if there is any pair or more than one pair of A equal to B exists inside of the relation, it is allowed in antisymmetric. Alright, from the example, we can see that R1 is not antisymmetric because it has 1, 2, and 2, 1. Alright, so for R2, R3, and also R4, R2, R3, and R4 are antisymmetric because there is no flip pair in the same relation. For antisymmetric, what we need to know is inside of the relation, both the A equal to B and also AB with the symmetric flip BA cannot be inside of the relation, meaning that the relation cannot have any flip of it, and it also cannot be A equal to B. So from the example, we can say that R1 and R3 is not symmetric because R1 has 1 1, 1 2, 2 1, 2 2, and also 4 4, and R3 has 1 1, 2 2, 3 3, and 4 4, which is obviously wrong in asymmetric. Last, let's look at transitive. A relation is called transitive if the pair AB is inside the relation and the pair BC is also inside of the relation, then the pair that connects from A to C must also be there for it to be considered as transitive. But for transitive, there are a few of conditions that you need to look at before you consider the relation as transitive. And for this case, you have to check every single pair because all of the pair have to follow the condition of transitive. Let's say that we have this relation here. How do we know that our relation is transitive or not? So we need to check one by one either the pair satisfy the condition of transitive or not. First, we have to look at the first pair, which here is 1 4, and label it as A and B, where 1 is our A and 4 is our B. Then we need to find a pair we start with our B, which here the B is 4. The only one that starts with 4 here is 4 2, so we can label the pair as BC pair. Now we already have our A, B, and C. Now we need to find a pair which connect from A to C, which based on the ABC is 1 2. If there is no pair connecting A to C, then the relation is not transitive. But here we can see that 1 2 is inside of our relation, so it is considered as transitive. For a second case, if the pair inside the relation have same element for A and B, meaning that it is reflexive, the pair is also and always transitive. Let's say we have a pair of 3 3, then our A is 3 and B is also 3. Now we need to find another pair that start with B, which is 3. But still, we're still gonna refer to the same pair, which is 3 3. Then we got now our A, B, and C are all 3. Then obviously, A connecting to C is also 3 3 because it's looping. For the third case of transitive, let's look at this example. This is a transitive relation. Why? Okay, so here we need to take the first pair, which is 1 2 as our AB. Now we need to find our BC pair, but there's no pair related to this one. So what we can say that there is no BC and also automatically no AC in this pair. So you have to remember that only if there is BC for your AP, then only it is compulsory to have AC. If there is no BC, the relation you have to remember, if you cannot find BC, it is always transitive. So same goes for the pair of 3 4.
Hi, next we are going to discuss about equivalence relation. So what makes a set is an equivalence relation? A relation on a set is equivalence relation if it is reflexive, symmetric, and transitive. So what is the properties of equivalence relation? R must be symmetric. Also, R must be reflexive. And R also must be transitive. How to do this question? So, let's take a look together how to solve the question. So, question number 1. Let R be the relation of the set of real numbers such that A are B if A minus B is an integer. So, let's take a look at reflexive. A minus A is equals to 0. It is an element of integer, thus R is reflexive. Next, symmetric. A minus B is equals to the element of integer. B minus A also equals to the element of integer. Thus, R is symmetric. Next, transitive. A are B and B are C, thus A are C. A minus B is equal to the element of integer. B minus C also equals to the element of integer. Thus, automatically A minus C is equal to the element of integer. So, R is transitive. Since all the properties are qualified, thus R is an equivalence relation. Is R a relation on the positive integers where A are B if A over B an equivalence relation? Reflexive. A over A is equals to positive integer, so R is automatically reflexive. Let's take a look at symmetric. A are B, then B are A. Thus A over B equals to B over A, for example. The 6 over 2 equivalents to 2 over 6. Of course, it is not equivalence. Thus, R is not equivalence relation.